So our little function 1 over 1 minus x representation in a power series n equals 0 to infinity x to the n is all fine and good, but it does have a limited range on what functions we can represent that way, because it's sort of got to look like that. You know, we can do a few things with that, but that doesn't get us like the sine functions, the trig functions. We'll be able to do trig functions with this next way. So anyway, that's hence where we're going with this. Taylor series is applicable to just about, I'd say, just about any function. We can represent any function with a Taylor series. You know, of course, it would some of them get complicated, but it is more generic than this. So anyway, that's what we do. And so the Taylor series is it has a form. What we do is we take a function, and to write it as a Taylor series, which is a power series representation, it's the summation n equals 0 to infinity. And then there's some notation here that we've used from time to time, not a whole lot, but as far as the derivative, if you remember, if you see a power, it looks like a power, but it's got parentheses around it, that means derivative. So this is the nth derivative at a. And I'll explain what a is here in just a second. Over n factorial. And then that's times x minus a to the nth power. So what this represents, like I said, this is a power series, if you think about it. You got your power, x to a power, that's what we mean by the power series there. But this is the Taylor series for f centered at a. That's what this is. So representing f as this, it's called the Taylor series of f, centered at a. And that's another kind of good thing here, because these, I don't think we did any where it wasn't centered at 0. These were always going to be centered up at 0. But these we can center them anywhere. We can do it at 2 or -10, wherever we want to. So that gives a little more flexibility there. But anyway, so that's what the A is. Like I said, this we'll talk about how we can come up with this. This is just the general, if we can, come up with a formula for the nth derivative at A. And then it always involves just divide by n factorial, and then, anyway, you'll see how we do this. So it's obviously more complicated than that, but it's more general, so we can use it more places. All right, so let's try one. Try one here. Let's find the Taylor series for f of x equals 1 over x, centered at a equals 1. Yeah, so this is the very first one right off the bat here, that one, yeah, we'd have a hard time using that form to do that, because in this form, you need to be a 1 minus x. That's going to be hard to do with 1 over x. So, anyway. So what we do when we start this, what we're going to do is we're going to start off and we're just going to start looking at derivatives of this thing. So we're just kind of do a little list here. And we'll start with, oh, before I do that, let's back up. Sorry. Hold that thought, because I did want to do one thing here first. Just to kind of get used to the notation, let me write out some terms for this. And so this. And so we start at n equals 0, and so if I write it out, that first one would be f, and then the parentheses 0 at a divided by 0 factorial, the n, I'm plugging in the n here, times x minus a to the 0, right? So I'm just, if I write them out term by term, I'm just plugging in n equals 0, 1, 2, and 3, so. Then the second term would be n equals 1, so I have the same thing, f parentheses 1 at a over 1 factorial times x minus a to the 1, right? So I'm plugging in all places to be 1. And then f, the next one would be f parentheses 2 at a over 2 factorial times x minus a squared. On and on we could go. Now, what I would point out here is these, well, let's start with this one first. So this means derivatives, and so that's normally not how we write that, right? We usually just do f prime. That's the same thing, it's just to make it, because once you get, usually we don't do, f prime, and then we do f double prime, and then f triple prime. Then after that, we don't really do the little marks. We go back to this, or do this, for the fourth derivative, and so on. So I'd point that out. Now, the other thing I'd point out, and that would be f double prime. Triple prime, and then, like I said, the fourth one. Now, what does this here? Well, that's the 0th derivative, so that's not a derivative at all. That's just the function at a. But, just kind of, and of course, too, you might know this, what's 0 factorial? You remember 0 factorial, and we could have simplified that one too, but this one really simplifies nicely, if you think about it. 0 factorial is 1, and then x minus a to the 0 power, that's 1. So all this amounts to, this first term is really just going to be f of a, okay? If you do all the simplification, and we could simplify some others along the way, but just be aware of those things. Okay, so I wanted to mention that. If we wrote it out, some things that, because a couple of them will have to write out that first few terms, or you'll see. All right. Okay, so back to this one. All right, so find the Taylor series for f of x equals 1 over x centered at a equals 1. The derivative of f of x, derivatives of, so we're going to just start out by doing some derivatives. And like I said, we're just going to start with the first term, the function itself, which of course, for derivative purposes, would be better to write as x to the negative 1. Just start doing derivatives. So the first derivative would be negative 1 times x to the minus 2. The second derivative would be 2 times x to the minus 3. Third derivative is negative 6 x to the minus 4. Fourth derivative, and like I said, that would be where we would go to that parentheses thing for derivative. Fourth derivative would be 24 x to the minus 5, with me there. And we could keep going, but I think that'll give us enough to figure this pattern out. Then alongside that, let's write the derivatives evaluated at A. So in this case, at x equals 1, in this case, okay? So we're going to kind of do two lists. First of all, just doing the derivatives in general, and then we're going to evaluate the derivatives at our particular A value, which in this case is A equals 1 or x equals 1. Okay, so that would be f of 1. And again, we're technically doing the derivatives, but we also need the function itself. Function itself value, it's part of the deal too. So it's f of 1, which would just be 1. F of prime of 1, so first derivative at 1 would be negative 1. F double prime at 1 would be 2, right? Because x is 1, so all this is 1s. 1s are here. So. F third derivative at 1 would be negative 6. And then the fourth derivative at 1 would be 24. So I'm just evaluating those, in this case at 1, because that was the A value. Okay. So, the reason we're doing all this is we're looking for this right here. Can I get the nth derivative at A in a general form? So that's why we do this. Can I get that expression right there? Well, I can see at least one part of this that we're going to need. The nth derivative is alternating signs. And so I've got to have that as part of my little expression here. Now, the question is, do I need an n or do I need another kind of an alternative thing to n there? Because I want the power, to be correct here. So the first derivative needs to be negative. It needs to be negative 1. The value of that needs to be negative 1. And then the second derivative needs to be positive 1. You see what I'm saying? This part needs to be properly sequenced. Okay. I think we're good with that because at n equals 1 we would have negative 1, and then at n equals 2 here we have a positive, so that would be squared. So that's okay. So that would be fine. Now the other part comes in, of course, with the numbers. Yeah, so these may not be as recognizable as they will be. 1, 2, 6, 24. Actually, those turn out to be factorials. Because if you think about it, that's how we're generating these. Because where did the 6 come from? Well, it came in because we did, right here, we did 2 times 3. And then the 24 was that 2 times 3 times 4. You see what I'm saying? It's a factorial. These numbers here are factorials. Even these two will be considered factorials. Now, the question is, does each of these equal n factorial? So this would be n equals 2. Is that 2 factorial? That's n equals 3. So is that 3 factorial? I believe so. Now it even works for the other two here. I started at 2, but it works for this one. This would be n equals 0, and 0 factorial is 1. This is n equals 1, so that would be 1 factorial. So this works for all n. It won't. There's a couple of times when it may not work for all of the n, but it works for all n here. Okay. So what that means is now we can write our function in the Taylor series format. So f of x is Taylor series is n equals 0 to infinity. I can get the nth derivative at a over n factorial times x minus a to the n. All right, so in this case, our f of x is 1 over x. Our nth derivative at a, well, we just established here, it's that. It's negative 1 to the n times n factorial. Then we're going to divide by n factorial. Hey, that's going to work because that's going to cancel out. And then times x minus a, well, again, the a is 1, so we're going to put that in. So we've got this pretty well, just do a little canceling here. So 1 over x, that power series representation is negative 1 to the n times x minus 1 to the n power. That's why we can represent 1 over x, and it's centered with the center at x equals. Center at x equals 1. Okay? So that's the basic steps. Do the derivatives, evaluate the derivatives at a, and then plug that in. Okay? All right. Try another one? Or two? Okay. All right, so let's find the Taylor series for f of x equals ln of x, centered at a equals 2. Okay. So we'll write that ln of x as that, and so first thing is we need to figure out what that is if we can. And so, yeah, let's just start off with our derivative list here. So we start with f of x equals ln of x. Then the first derivative is 1 over x, right? What's the second derivative? Well, to get the second derivative, I'd probably say, well, that's x to the negative 1. And so then the second derivative is easy. It's just negative 1 times x to the minus 2. And then the third derivative, this is looking familiar, isn't it? Positive 2 times x to the minus 3. And then the fourth derivative at x would be negative 6 x to the minus 4. And I think you see what's going on here. Fifth derivative would be positive 24 x minus 5, a lot like our other list now, but some slight variation. All right, so now let's evaluate these at a. In this case, a equals 2. So f of 2, ln of 2. F prime of 2, well, it'll be 2 to the negative 1 or 1/2. I'm going to put it. F double prime of 2 would be negative 2 to the negative 2, but that's going to be negative 1/4, isn't it? F triple prime at 2. It's 2 times 1/8, which that reduces, but I would not, for purposes of getting it, the expression here, I would probably not reduce that. Fourth derivative at 2 would be negative 6, then 2 to the negative 4 would be 1/16, so it would be 6 over 16. And again, it reduces, but I would leave it not reduced, because eventually they won't reduce. Like here, well, I guess it still reduces, but I guess they will reduce, but I wouldn't reduce them. Yeah, okay. Because they all reduce differently. Anyway, all right. So the question is, can I come up with an nth derivative at A expression for this one? Well, once again, it looks like we got the alternating signs. Now, the problem is, I think on this one, -1 to the n actually won't work because at n equals 1, I need it to be positive 1, right? It needs to be a positive 1. If I just leave it -1 to the n at n equals 1, that would be -1. And so I need to make a little bit of an alteration there. And you can either do n plus 1 or n minus 1. That won't matter. If you do n minus 1, you get the same thing. But you see that then will match it up because at n equals 1, I would have a positive 1 for that. At n equals 2, I needed it to be a -1. And so at n equals 2, it'd be -1 cubed, which is a -1. So that'll get the right sequence there. Okay, so we have to do a little adjustment on that. All right, now what else do we see? Well, there's a couple of things going on here. And that's why I didn't reduce it, because look at the top number. The top number are those factorials, aren't they? So the top number here is a factorial. Now, is it n factorial? I don't think so. Because look at this. At n equals 3, I've got the top number is 2. That's not 3 factorial. At n equals 4, it's 6. That's not 3 factorial. I mean, that's not 4 factorial. It's 3 factorial, isn't it? Yeah. And at n equals 5, that's 4 factorial. So it's not n factorial, it's n minus 1 factorial. Now what about the denominators? Well, the denominators, 2, 4, 8, 16, 32, recognize those? Powers of 2, isn't it? That's powers of 2. So it's, now is it 2 to the nth power, to the first, to the second, to the third, to the fourth? Yeah, I believe so. That is 2 to the nth power. So that's a pretty good formula, except it doesn't work for all n. It works for all of them, except which one? The top one, n equals 0. So we'll have to make an exception here. Okay? With me on that? Any questions or concern? How we got here? All right, so now that's what we're going to plug in to here, except not for n equals 0. All right, so f of x equals, and so I'm going to pull out n equals 0 separately, and so that would be, again, f parentheses 0 at 2 divided by 0 factorial x minus 8 and a 0, which again, a lot of that's going to go away, but you see what I'm getting at here? Then I can put in my generic form for n equals 1 to infinity, because this is going to work from 1 on, 1 to infinity. So that would be -1 to the n times n minus 1 factorial over 2 to the n. And we'll divide by n factorial, because that's the part that comes from the Taylor series here. So I just plug in what I found there, right in there. And then times x minus a, which a here is 2, to the n. And we'll just clean that up a little bit. So yeah, this 0 factorial is 1, x minus, that would be a is 2. But it's not going to matter because that's just 1. So on the left here is f of 2. Well, f of 2 is ln 2, so That first term is ln of 2. And then the rest of it, let's see what happens. Well, that 2 to the n will be down here with the n factorial. If that'll work. But then I do have a little bit of factorial stuff I can maybe do a little canceling on. How's that going to cancel? Because I don't think we've had it where we had an n minus 1 factorial. How's that going to cancel with the n factorial?
N factorial.
Let's do it over here. Well, couldn't I write n factorial as n then times the next term would be n minus 1, so that would be, the finish would be n minus 1 factorial? Yeah, so this is going to reduce out and just be an n right there, isn't it? Okay. How's that? Question? One thing, just to notice here on my notes, sometimes, oh, this is n equals 1. Sometimes they'll do a couple of different things on this. One thing maybe we'll see is this. I mean, if you don't do this, that's fine, but just FYI, book might do something like this for their answer. Since both of these are the nth power, I can combine those and make it -1 times x minus 2 to the nth. See what I'm saying there? Since they're both the nth power, we could, oh, but that's not the case, is it? Never mind. I did that wrong. This is n plus 1. So here's what they might do. Yeah, that should be n plus 1. I missed my power up there. So if we did something like that, here's what would happen. That would be n equals 1 to infinity, -1 to the n times -1 to the first. Then we can combine that, what I'm going to show you. So we have ln of 2 plus just another version of this answer. All right, so we'd have to leave the -1 here. But anyway, when I combine these, I can multiply the inside parts, and that would make it -x plus 2, which is another form we could have. But what they also might do is rewrite that as 2 minus x to the n. So anyway, if you see something like that, that's probably what they did. Instead of x minus 2, they put in 2 minus x. Well, they probably combined those two things together. So anyway, they'll do some things like that. Okay? All right.